All right, let's jump right into it. If you're an environmental science or geography undergrad trying to wrap your head around how we actually map the Earth, this explainer is for you. Today we're digging deep, pun intended, into the really fascinating world of digital soil mapping.
So, here's the big question. To do precision agriculture right, and to make sure we aren't over-fertilizing our lands, we absolutely need highly accurate soil data. But think about it for a second. Physically surveying and digging up every single inch of a farm? That's completely impossible. I mean, that would bankrupt a farmer practically overnight. We literally can't dig everywhere. So how do we know what's under our feet? Well, we have to predict it. And the ways we actually make those predictions, they've evolved in some pretty wild ways.
Okay, here is our roadmap for today. We're going to cover 1. The Core Soil Mapping Challenge, 2. Classic Geostatistics, 3. The Machine Learning Era, 4. How we combine forces with hybrid models, and finally, number 5, Uncertainty and Validation. Let's get going.
The Soil Mapping Challenge.
Imagine taking a giant mathematical grid and just laying it directly over a really complex, bumpy physical landscape. That's essentially what we're doing here. Our entire goal is to predict soil properties, things like organic carbon density or, say, clay content, at all those specific grid locations where nobody actually went out and took a physical measurement.
To pull off these predictions across that massive grid, we rely on math. Specifically, we're looking at the mathematical relationships between the few actual physical soil measurements we do have and a whole bunch of environmental covariance. You probably know these as the founding fathers of soil formation: climate, relief, organisms, parent material, and age. And these days, we are capturing massive amounts of this environmental data using remote sensing, satellite imagery, and digital elevation models, and then feeding all of it straight into our predictive models.
Moving on to Section 2, Classic Geostatistics Methods. For decades, ordinary kriging was the absolute go-to classic method, and it relies entirely on geographic proximity using a concept called spatial autocorrelation. Now, that sounds fancy, but it's basically just mathematically modeling a very logical assumption. Soil samples that are physically closer together are naturally going to be more similar to each other than ones that are miles apart, right? It leans heavily on the natural underlying spatial structure of the environment to essentially fill in the blanks. But there's a catch. As our datasets got bigger and way more complex, mostly thanks to that massive explosion in remote sensing technology we just talked about, classic geostatistics really started to struggle. These older models just have a terribly hard time capturing intricate, nonlinear relationships. Plus, they rely on really strict assumptions about the data being normally distributed, which, let's be real-world soil almost never is. The result? Ordinary kriging tends to generate maps that are just way too smoothed out. They completely miss those highly localized, tiny variations that are absolutely crucial if you're trying to do precision agriculture.
Which brings us to Section 3, the Machine Learning Era.
To handle this absolute tsunami of complex environmental data, soil scientists pivoted. They turned to machine learning. Tree-based algorithms became the new heavyweights, especially one called random forest, and it's exactly what it sounds like. It generates multiple decision trees, literally a virtual forest, to vote on those hidden nonlinear relationships between the environmental factors and the soil properties. It is incredibly resistant to overfitting, and it effortlessly digests massive, noisy datasets without breaking a sweat.
So, as students in this field, you're essentially looking at two competing schools of thought here. On one hand, you have geostatistics. It understands spatial geography and proximity perfectly, but it's pretty terrible at juggling massive, complex datasets. And on the other hand, machine learning. It is an absolute powerhouse at finding patterns in huge mountains of data, but it's often completely geographically blind. It doesn't inherently understand that two pixels sitting right next to each other on a map should probably be related.
All right, Section 4. Combining forces, hybrid models.
Eventually, scientists realized, why choose sides? This brings us to a process called regression kriging, which is a true workhorse of modern digital soil mapping. It literally gives us the best of both worlds. Here's how it works. Step 1. The machine learning algorithm predicts the overall soil trend based on all that environmental data. Step 2. Because that ML model totally ignored spatial proximity, it's going to leave behind geographical errors, or residuals. So we use ordinary kriging to map out those remaining spatial errors. Step 3, we just add the two together. Boom, you get a highly accurate, spatially aware map.
But the innovation actually didn't stop there. Lately, researchers are testing out something called kriging prior regression, or KPR. Instead of fixing the machine learning errors at the very end of the process, KPR completely flips the script. It treats the kriging spatial data as just another input feature, feeding it directly inside advanced AI foundational models like TabPFN. And this inverted approach, it is insanely robust when your field samples are limited, which happens all the time in precision ag. In fact, it's been shown to boost predictive accuracy by roughly 30% compared to just using standard machine learning on its own. That is a massive jump.
Finally, Section 5, Uncertainty and Validation.
Here's a hard truth for you. No map is perfect. In soil mapping, uncertainty is really just an acknowledgement of error. Because soil variation is so unbelievably complex, and even our most precise physical lab tools have margins of error, we just have to accept that our digital representations will always differ slightly from the real world. Honestly, explicitly expressing that uncertainty is a non-negotiable part of the scientific process.
So to figure out exactly how accurate our fancy new hybrid models actually are, we have to rely on statistical validation. We literally take the predictions our models spit out and we compare them directly against actual observed field values. This is what gives us those global quality measures that summarize the accuracy of the entire map.
But where do we get those observed values for the comparison? Well, researchers usually have to make a really tough choice here. They can do additional probability sampling, which means going all the way back out into the field to dig a brand new, highly expensive soil survey just to test the map. Unbiased? Yes. Cheap? No way. Alternatively, they can balance their budgets by using data splitting. That's where you take your existing data set, use 75% of it to train the machine learning model, and essentially hide the remaining 25% in a vault to use as a test later. It is way cheaper, but you obviously need to have a big enough initial data set to split it up in the first place.
So as you continue your studies in environmental science, I want you to keep this one thought in the back of your mind. As our hybrid algorithms and foundation models get smarter and smarter, simply generating the map, that's only half the battle. The true challenge you're going to face out there in the field is determining exactly how close to perfect our maps actually need to be in order to optimize precision agriculture, protect our fragile ecosystems, and ultimately save our soils. Thanks for joining me on this explainer. I really hope this helps you map out your future studies.